Hi, in this video, we are going to simulate a sample problem in Principles of Chemical Engineering Processes by Gasson and Henda. Specifically, example 6.2, ammonia reactors with recycled stream. The problem is, nitrogen and hydrogen gases are fed to a reactor in stoichiometric quantities and react to form ammonia. The conversion of nitrogen to ammonia is 25%. Since the single pass is low, we decide to separate the product stream and recycle the unreacted gases back to the reactor. How much nitrogen is required to make 245 kilomoles per hour of ammonia, and what is the flow rate of the recycle stream? So we have a diagram here for our problem. The feed nitrogen and hydrogen flowing into the reactor and the product being separated into pure ammonia at a rate of 245 kilomoles per hour, and the unreacted gases, nitrogen and hydrogen, back to the feed stream. We also have the reaction for the production of ammonia given by 1 mole nitrogen plus 3 moles hydrogen to form 2 moles ammonia. So to start, we have a basis given by 245 kilomoles per hour of ammonia produced, and in the problem it is stated that the feed nitrogen and hydrogen are supplied in stoichiometric quantities. So before simulating, it is best that we solve manually first so that after simulating we can validate if our answers are correct. So to begin, looking at the the diagram, um, we can solve for the we are going to solve for the streams 1 to 6, and looking at the diagram, we can solve for streams 1 and 2 by applying an overall mole balance on the system, um, which would be given by the amount of moles entering the system equals to the moles leaving the system at the rate given by 245 kilomoles per hour. So the overall mole balance for nitrogen is 2 moles nitrogen multiplied by the flow rate equal to 1 mole of nitrogen times the flow rate of 245 kilomole per hour. Solving for N1, we get 122.5 kilomole per hour. And for the mole balance of hydrogen in the system, we have 2 moles of hydrogen multiplied by the flow rate equal to 3 moles of hydrogen multiplied by 245 kilomole per hour. Solving for N2, we get 367.5 kilomole per hour. We now have our values for our stream 1 and stream 2. And looking at the problem, we can use the conversion of nitrogen to ammonia and the stoichiometric ratios given by the reaction to solve for the quantities of the gases in stream 3 and stream 4. So looking at the conversion, which is 25%, we can get the total number of moles entering the reactor, nitrogen fed to the reactor, which is equal to 122.5 the total moles of nitrogen divided by the conversion 25% or 20.25, which gives us 490 kilomole per hour. From this, we can also solve for the unreacted moles of nitrogen that leaves the reactor. This would just be equal to the total moles into the reactor minus 122.5, which is equal to, we get 367.5 kilomole per hour. We now have our value for the composition of N2. We now have to get for the hydrogen. So to get that, we basically have to look at the stoichiometric ratios provided by the reaction. We can see that 1 mole of nitrogen plus 3 moles of hydrogen reacts to form 2 moles of ammonia, which basically means that we need thrice as much hydrogen to react with 1 mole of nitrogen to form our product. So the total moles of nitrogen needed for the reaction would just be equal to 3 times the amount of nitrogen, which is 490. And we get 1470 kilomole per hour. And from this, we can also get the total moles of unreacted hydrogen from the reactor. We have 1470 minus 367, which is our total moles in our feed. And this would be equal to 1102.5 kilomole per hour. So now that we have the values for the composition of our streams 3 and 4, we could put that in a summary in a table so that we can get a total view of our streams. So for N1, for stream 1, we have this amount of nitrogen, 122.5 kilomoles per hour, and we don't have hydrogen and ammonia. And in our stream 2, we have no nitrogen and 367.5 kilomoles of hydrogen and still no ammonia, since this is our feed. For stream 3, which is the amount of moles, total moles being fed to the reactor, we just add these values here, the total moles of N2 and the total moles of H2, both being fed to the reactor. So we have for nitrogen 490 and for hydrogen 1470. This, and we still have no ammonia, which gives us 1960. For our stream 4, which is the stream from our reactor, um, we add our values here, which is the unreacted moles of nitrogen and hydrogen. Also take note that this stream already contains our ammonia, and it is given to be 245 kilomoles. So here in our table, we put for nitrogen, we have 367.5. For hydrogen, we have 1102.5. And our ammonia from the reaction, we have 245. This gives us a total of 1715 kilomoles per hour. And our product stream 6, is which is the separated pure ammonia. We just input here the value for ammonia. For our recycle stream, we take note that in our problem, the unreacted gases and the ammonia are being separated. So basically, this stream here is being split into the unreacted and the ammonia. So the amount of unreacted gases is just equal in both streams since they are only separated. So we have for the number of nitrogen in our stream 5 or recycle stream is just equal to our stream 4 or the stream from our reactor. So 367.54 nitrogen and 1102.5. We have no more ammonia since it is already separated. We then have a total of 1470. We can also get this value by applying a balance here at our distillation unit. So applying a balance which is amount in should just be equal to the amount out or leaving. We have stream 4 that's going in. The streams going out are N6 and N5. And we need N5. So solving for N5, we just need to subtract N4 N6 from N4. So N5 would be equal to 1000. I am sorry. Subtract N6 from N4. 1715 minus 245, which gives us 1470, which should just be equal to here. So now that we have the values for our streams, we can then proceed to simulating our problem in DWSim. So in our configuration, we put in our compounds, nitrogen, hydrogen, and ammonia. For our property package, we use Reel's law. And for our units, in the problem, it is the values are stated in kilomoles per hour. So we could use this since it is given in kilomoles per hour. For our reaction, we add a conversion, which we name ammonia production, and we include all our compounds, and the base component would be nitrogen. And for the stoichiometric coefficient, we take note that for products it is negative, it is positive, and for reactants it is negative. So recalling the reaction, we have 1 mole of nitrogen reacting with 3 moles hydrogen to form 2 moles ammonia, taking note of the sign convention. So the reaction is balanced, and we also put in the conversion given by the problem to be 25%. Okay, so we then proceed to um, basically following the diagram. So before anything else, we should stop the flow sheet from solving so that we can avoid unnecessary calculations. So to also avoid confusion, it is suggested that you um, put first the units or the blocks before the streams. So in the diagram we have, and in the problem we have a mixer. Um, we have a reactor, and we have the distillation unit. But in in this case, for our simulation, um, for simplicity, and since it is not given in the problem, the specifics of the distillation, like um, the configurations, we could just settle for a compound separator, since it is also stated in the problem that the products are just separated. We could just name this as a distillation unit for coherence to the problem. We then we then begin by inputting the streams. So for our in our mixer we have the streams nitrogen and hydrogen. Then we have the outlet stream, which is being fed to the reactor. We set that as the inlet stream. And oh wait, I forgot. In the reaction, we also need to specify that the phase of the reaction uh, is in the vapor phase. So we have the outlet stream and also the energy streams. And this stream here we connect to the distillation, since this will be the stream that will be filled with our product. And our outlet stream from the distillation unit, we have the pure ammonia and the unreacted gases that will be recycled back to the feed. And for a recycle stream, we use logical um, logical ops recycle block. We connect that to our stream, and an outlet stream, which is then being fed again to the mixer. Okay, so we have to specify in our nitrogen stream that it is only pure nitrogen, and in our hydrogen stream we also have pure hydrogen. And since we already have solved for the flow rates of our nitrogen and hydrogen streams, we could just input it here. For our nitrogen, we have 122.5 kilomoles per hour. And for our hydrogen, we have 367.5 kilomoles per hour. And what else? In our separator, we have to indicate that in this stream, we will the flow will just be equal to the nitrogen and hydrogen, and for the outlet stream 2, what will be left will just be the ammonia. So we set the separation factor specified for outlet stream 1, which is this stream, which should contain our nitrogen and hydrogen. So we set the value for molar flow, and this is since in DWSIM we don't have a value for kilomole per hour. What's closest is the moles per second. So how do we get this value? So um basically we just take, we know that for this stream, for the nitrogen and hydrogen, the outlet stream 1, we have a value of 1470 kilomoles per hour. So we just need to multiply it by the composition or the conversion of the gases as stated in the problem, which is 25% for nitrogen, and we have 75 for the remaining 75 for hydrogen. So we have wait we have for our nitrogen separation value, we have 1470, our recycle stream, multiplied by 0.25 from our conversion, and we need to since this is in kilomole per hour, we need to multiply it by, convert it to moles per second by multiplying it with 1000 over 3600 to get moles per second, which should be equal to 102 point 0833. That is for our nitrogen separation value. For our hydrogen, the remaining it will just be equal to 75%, and this would give us a value of 306.25. So take note of these values, and then we plug that in to our separator. For nitrogen, we have 102.0833, and 306.25. So we recalculate before starting the simulation, and I think we have inputted the necessary data. So let's try and running the program, the simulation rather. Hmm. Ah, sorry, forgot the energy stream. Okay. Okay, so the simulation has run, and for we should have our manual calculations should coincide with the simulation. So for our product stream, we have 245 kilomoles per hour, which is what is given in the problem. And for our nitrogen feed, we have 122.5 kilomoles per hour, again stated in again, which coincides with our calculation. And for the recycle stream, we have 1,470 kilomoles per hour. Um, we can further validate our simulation by looking at this is our stream 3 based on the diagram, and this is our stream 4. So in our calculations, we have solved for stream 3 to be 1,960, and in our simulation we got 1,960. And for the stream 4, we have 1,715, and in here we should get the same value, 1,715. So that's the simulation for this problem. um, Thank you.